Hello everyone. We are starting today's lecture. Today we are going to continue with some special types of limits, but this limit, I would say that even limit, this universal construction has special names, and this name is these names are n and co-n. So let me start with a motivational example. It will be very big example. So part one today is and correct. Okay, so we have an example. For any set A, B, there exists a bijection which tells us that every function of two variables can be considered as a family of functions of one variable with values in a set of functions of another variable. And conversely, every function, every family of functions that are parameterized by some set can be considered as a two-variable function. So here in this case, I will set L to be a functor length comma b. I will set R to be a functor set e comma blank. So this is a Cartesian product functor. This is a functor of that takes all functions from set B to some fixed set, to the set that we will put as an array. And we have in this case the usual adjunction. So set of LA to C, set A to RC. Very well. Then we can consider a co-unit for this adjunction. So co-unit, as you know, is a natural transformation from a composition LR to identity functor. Identity functor on set, as all our functors are between sets. Okay, so how it will work? So epsilon of x is a map that first we apply R to letter x to our set. So R of x, it will be R. I need to overlook focus. It will be a set of all maps from B to X, and then we apply functor L. So we take a Cartesian product with B. Then we should land in X. And if you will look carefully in the definition, how we will, what is a bijection, how it will correspond from two variable function to family of one variable function parameterized by set A, you will see that epsilon of x is the following. The pair f comma b, where f is a function from b to x and b is an element of b, the element goes to an evaluation f of b. So here is our epsilon x. Epsilon x is a component natural transformations LR to identity function called F. Up to now, the story is all usual. We know this very, very well. So it's natural transformation and naturality is invariable X because it's a natural transformation between functors of one variable. But we see that there is a present another variable called B. Moreover, it's presented twice. So we can assume that here could be some B1, here can be some B2, they're somehow related, and in a certain way we can get here in X. So in this formula, we have more than one hero who is X. We have also B, or maybe different B's in this could be. So then, I will write everywhere in parentheses B. Okay? For our F. Because it depends on B. If we will have another set, not B but B prime, it will be epsilon superscript B prime. So this is natural in F and not natural. You can easily check it by direct computation. There is no naturality in B at all. However, there is a certain weakened notion of naturality that follows. And I will write it down. So, for any morphism from set B, B prime, we can write that set prime comma set comma X. Here will be X. This is a component of transformation F2 superscript of prime that component there. This is a component of natural transformation. That component epsilon of superscript B of X. And they are related by two different morphisms. One morphism change here B prime to B in a contravariant way. Another change this B to B prime in a covariant way. So here you can observe that B, second B is covariant and first is contravariant. As first is standing on a spot of a contravariant variable in a home set of function. So this guy on the top will be called precisely F comma F from B. And this one here will be set B prime comma X from F. You will ask me, okay, how do they all act and align together? I'll tell you. very easily. So when we have a map prime from B prime to X and elements of B, and I want to apply F prime to B, what should I do? If I know with my F, that my F is fixed. First of all, I need to take my B, element B, to the set B prime using F, and then apply F prime, and I will land in X, so here. But I can do this in two different ways. First, apply F, then F prime. Second, first compose functions, and then apply them to B. And these two different ways are described here. So let's write them down. So this will be B, X, comma B. Here will be F prime F. Here's B prime square F prime, comma FB. And they are both F to F prime F. Or we can say something that is weaker than naturality, but still is valid. Still is valid and is rather interesting. So we have certain condition on a functor which has two variables, one contravariant, one covariant. And they are coming from the same domain, right now from set. This situation was generalized to a notion of so-called denatural transformation. Yeah, take a picture anytime you want. Also, if you are quite lazy, you don't like to write, you can always take pictures of me or board whenever you need it. Okay? As for certain lectures in my life, or seminars, I was quite lazy. I'm taking pictures whenever I want. Of course, if the speaker allows, so I'm by default allowing anything. So let's give me a definition of denatural transformation. I don't know. So alpha from P to, I'm writing such arrow, so arrow with a diamond at the end, not arrow, to Q, which are both functors from category CO cross C to category D. It's called transformation. If for any f from C to C prime, the following diagram commutes. Wait, I did a small inaccuracy. So alpha is the natural transformation, and given by a family alpha sub C from PCC to QCC. Family of maps which has just one subscript, and we have here of natural transformation epsilon evaluation of function at the point. So we are taking both variables to be the same. So here we have they have just the same name. So the natural transformation is given by a family of such maps between the, let's call them diagonal values of a functor. So functors P and Q are going from a product of category C open C to category D, but we always can take both arguments to be equal, covariant and contravariant, and these values will be called diagonal values of functions. So these are diagonal values. So our natural transformation alpha is a family of maps between diagonal values of functors P and Q such that for every function f, not function, excuse me, morphism f from C to C prime, the following diagram commutes. This will be quite a big hexagon. So here we have alpha C prime, alpha C. Okay. Just think about natural transformation because something will be missing and we will replace it. So in natural transformation, we were going from values of a function, first function, to the values of another function. Here we are going from diagonal values of one function to another. And this component C prime, should be somehow related by this function f. Excuse me, I'm always calling function by morphism f from C to C prime. So I need, remember in my example, to join them somehow with these two things, like mixed values. How I will do this? I will do that using this diamond-shaped diagram. Here will be P at C, here will be P C prime F, here is Q C F, here is Q F C prime. So this thing commutes. Well, you will first ask, are the natural transformation features and natural? The answer is yes. So every natural transformation can give us the natural transformation. Okay. So we can, from a definition of natural transformation, derive such a thing. Well, we can try to do this even now, if you want. Spend a couple of minutes. Okay, let's do this. Remark. So alpha is the natural transformation. And for every x, right, we'll have we'll break our diamond in 3 pieces. 2 squares or parallelograms in this case will tell us that alpha is a natural transformation. And the last one, third piece, will tell us that Q is a bifunction. So let's do this in this spiral. C prime C. Here will be P prime prime P C C, Q, DC prime. Q. If I will fail, it will be a formula. If I will forget some moment. So here. Here should be something. Okay. So here is PFC. Here P, P prime F. Here is alpha. Components of natural transformation are given by two variables. So here will be alpha C. Here will be alpha C prime C prime. Since we assume right now in the remark that we have natural transformation, and I want to show that natural is finished. So I need to prove that the outer hexagon commute. So here it is alpha CC Q alpha prime C to prime C. Here will be Q FC. Here will be Q prime. Here I have Q CF. Here Q prime FC prime. So actually, with the down, we have arrow to F. So this is by naturality of alpha. Here is against naturality of alpha. And the lower one is by functoriality. And by factor, the factor everywhere. Hence, alpha from E to Q natural transformation gives us alpha natural transformation from E to Q, whose alpha sub C are given as alpha sub CC. We have an example. The easiest examples are coming from a case when one of P or Q, one of these factors are constant. So suppose that P from C of C D takes pair C1 going to T. It's F1 to top. Then in this case, for every f from C to C prime in the diamond, in this hexagon, 1, 2, 3, the top 3 objects will coincide with an object D. And instead of hexagon, we will obtain a square. So there we'll have Q. Q prime, Q C prime, C prime, Q C, C prime, Q. Here's object D. So there's Q F C prime, Q C F. And this is commute. Okay. We can call this factor the constant factor with the value D as we did last time.
Sorry, Alex, what is Q here in this example?
Q is the same factor from C of cross C to D. Okay. So here Q. Cross any factor. Diagram, well, have. So in this case, we will write that we have delta sub D, the natural transformation to Q. Such natural transformation is called batch. If you write with let's call it, I don't know, tip or with a tip. This is a substitution of the things that we learned last time. This is a substitution of a cone. So if for natural transformations we had cones, and cones were given by natural transformations from a constant factor to your factor, in the case of denatural transformations, you are talking about edges with a tip D, and its base is Q. However, I need to remark before you will ask you a question. When we had cones, cones had a base of all values of our factor on the diagram and all arrows. Right now we do not have it. Right now we have only diagonal values in the bottom. So as you see, if it's alpha, here will be alpha C prime. Right now you have that my legs of wedge are landing in diagonal values of the function. And between them there is no direct correlation. There is indirect correlation. In case of limit, we had just an arrow between every two values, right? In the diagram in the bottom. Here we will have like intermediate guy who is mediating them. Okay. So this is a wedge. Between wedges, there is a relation. So we can compare it to wedges, right? If I have a wedge here D, I can have another wedge D prime. So if I have D prime, here will be beta C prime. So Q C prime C prime. with beta C. And I have here my D, previous one. Here's alpha C, alpha C prime. So I have two wedges that both length in Q. If I have here Q, here is my alpha T, alpha D prime. Alpha, well, wedge beta. When I have a map H from D to D prime, I will get a natural transformation between constant factors. It will be delta sub H. And composition of natural transformation. With D natural transformation will be D natural. And we will be giving me precisely my alpha. Wait. Did I do this right? Yes. So we have a category wedge of Q whose objects are wedges and morphisms. Morphisms are given by D to D prime such that the triangle star
And here you fix D.
huh?
The D is fixed.
Well, objects are given by all possible D.
Oh, okay.
So if you find such D's that there exists a wedge, it's okay. So your objects are natural transformations. The natural transformation should start from a constant function. So you fix the base Q. And this delta sub E, they vary. And they are aligned to each other using the morphisms from D to D prime. So they classify them. And these morphisms are not random. This morphism should satisfy this triangle or this diagonal, which is the same as this triangle below. So before we had cone, and which cone was lower? The one to whom we have an arrow. Okay?
And I presume that should be the diamonds. And then into Q.
Yes. Of course. Definition. We'll continue our example number 2, but only after the definition. Definition. Terminal voltage where Q is called an M. So the wedge through which everything factors notation. We will write Q or integral QCC sub C, or sometimes just integral sub C of Q. Isn't it nice? You will ask me, no, of course it's not nice, because we don't know what to do with this integral. After this, right now, I will define what is a coin. And later, the whole course and whole category theory will be written in terms of ants and coins. That is called coin calculus. So ants and coins play the same role as sums and products play in analysis. Veg, not veg, ant, is an analog of infinite product. And coin that I am going to define, dual, completely dual, is an analog of infinite sum. In analysis, we are usually working with sums. So we are making partition of certain domain, of some simpler regions, and integrating, so taking like the area by the value over this area, so certain average value of whichever. And then making summation of all our elements of partition and taking limit. So taking limit and taking terminal. So our veg would pretty much substitute, but in this case, not summation, but product. So instead of talking about integrals in terms of limits of sums over partitions, you could also think about limits, or more precisely, co-limits. No, exact limits of products. So this is infinite products. Co-limit will be infinite sum. So this will substitute something that's not really too much used in analysis, or super used in algebra. The co-limits that I'm going to define will be precisely what is integral, but in a categorical way. And both of them can describe well, almost everything what I have up to now. Unit dilemma, Ken extensions, adjunctions. So if something can describe unit dilemma by the famous phrase of Auslander, as I remember, Alex Marcinkovsky can correct me, if something in category theory cannot be derived just from unit dilemma, applied so many times as you need, then it's very likely that it's wrong. I would say that categorical statements are usually categorically trivial. So the main thing, it's not my statement, it's statement of John Gray, big guy in category theory. So in category theory, usually statements are just observations. Then you observe something, and then you're trying to really ensure and prove it. But it's not really a proof as you do in analysis. There are very few things that are really like hard worked and proved, and then finally inside what we are getting. The things are usually observed and then justified. Here, in the beginning motivational example was an observation, which was justifying our interest to this hexagon. Right now in this hexagon, I'm going to squeeze lower three Q's together and obtain coverage. And then initial coverage goes to called square. So all the intrigue is away. We just need to take and go forward. You can initial transformations. From P to delta plus E. So delta is called coverage of P. Let's call it pole tip. If tip for coal, then co tip for pole. C. Here will be P and C prime, C prime, C prime F. Here will be my D, alpha sub D, alpha sub C prime, alpha sub C. And we have a comparison. Natural delta delta D prime. And delta here is beta. Wedges. Dimorphism from F to beta is given by H. That's the double star here. Here is your double star diagram. Or if you write it down, delta. Right. Here is delta. Definition. Initial voltage. Great. I'm not defining it, define null. Is called coends of the notation. Notation. Coend integral superscript C of P C, or just integral superscript C. I won't be saying probably integral O, but sometimes good. I will be calling them coend and n perspective. So n over C and coend over C, where C is our key. Oh. Then we're going from the construction to properties. Property. Property number 1, functoriality. Property number 1 is functoriality. So if we have the natural transformation alpha, we have a morphism from n over c of FCC to, let's call it LTC. And C, and the same for n. Yes, this morphisms. This correspondence, respect composition, respect identity, so on. So in other words, we will have that n over c, coend over c and n over c are functions from a functor category C of cross C category modulus. You can also write when C is small. Modularization, so I'm not thinking or talking whether functor category is really a category. As have you seen in the morning, who was participating in the morning talk of Alex Marcinkowski, he was emphasizing that natural transformation between two factors with a fixed domain codomain usually form a proper class. Not always, but usually. There are certain cases, as he said, when the first factor is finally generate another factor is arbitrary, then we will have a set, but that's just one case. There are certain results that allow to say when the factor category is really a category, but they're not part of our course. If you would be interested, I can provide you certain details, and then from that point you can start picking up. There is a paper of so-called Linden author, and Linden refers the result of Kelly or McLean, I forgot whom, who developed certain theorems. When you can, in certain cases, using certain adjunctions, say that functor category is a category, but that's quite open topic. Okay. Then second property. For ends as for let's call it. So for n to functor, sorry, n to functor f over c is a isomorphic Taurian limit from a twisted arrow category of C to category C of C to category D. Now factor f, and here is a product. Here is domain plus codomain factor. So what's going on? Who are objects of twisted arrow category? X arrow from X to Y, called F and Y. Morphisms from X op to X prime op, from Y to Y prime. This is called X small op. This is called Y. Here will be arrow F prime from X prime to Y prime. Here will be Y, here will be X. So these are morphisms between two objects. That's how look morphism between two objects in a twisted arrow case. Then this pair of objects and morphism between them will go here using domain codomain function. We'll go just to X of cross Y, sorry, pair of Y, and morphism to X prime of Y prime. Here is X of comma Y. So we are just forgetting that the middle should commute. We are kicking it out. And then we are applying factor F. So here will be F. x prime, y prime, and between them have of x and y. Co-limit is given similarly. So coend of CC, it will be a co-limit. And you remember that limits in an opposite category are upper limits, and co-limits in opposite category are limits. So we need everywhere to substitute C by C op. But also then to change here DOM to DOM op, codomain to codomain op, and here will be double, like how many times? So here will again be C op, C, and there will be F. So here is twisted category, arrow category of C op, again taking op of it, going to C. So here should be C op, but then we are again taking. So C op, double op, and third time op, so it will be again op. So it's op because of 3 times. Here to C. Here is again factor F. Here will be domain op, codomain. What this is a category where both these arrows are upside down. So morphism from F to F prime will be given by arrows that are going upside down, and then we are taking opposite of that category. Just to land here. Therefore, coends and ends are particular cases of co-limits and limits. But don't be so excited, as it all works nice in a case when we have what? We have sets. We have ordinary category theory, because here we have category of elements. That's marked. Category of elements from of a factor home. So when the category of elements exists, and 4 factors landing in set it exists, then we can do this thing. Otherwise, we can. In an enriched category theory that we will start next time, we for sure won't be able to do that. So ends and coends will get much more powerful. And limits and colimits will be defined using ends and coends. Okay. Then, as I said last time, to have a limit, it is the same if we have all products and equalizer. To have a co-limit, it is the same as to have all co-products and co-equalizer. Did I give you a formula last time how to compute it? No. Well, because I wanted to spend time and prove the theorem, but I cannot have this thing right now, this time. But still, I will give you a formula as how to write ends and coends in terms of equalizers and co-equalizers.
Sorry, just one thing. What does that rotation mean?
Category of elements.
Category of elements of that's just the
morphism. Home factor. It's a home factor, so first variable. First place, second, and second. It's a home set. Home set. So, co and as co equalizers of co excuse me again, I'm all the time mixing up. End of factor f is a solution to equalizer of. Here we are taking product over all diagonal values. And here, on the other side, we are taking product over all morphisms in category C. So we have two arrows. First arrow is a product over F of F, right? And second, the product over F. So what do? You are mastering a map from this product to a single component. And then, if you have a bunch of maps from one object to the set of objects, it's the same as to give one map from this beginning to the product of all the ends. Here are the products of all the ends, that's why it's written. Please close the parentheses. So what we do? We do the same as I was explaining before, that from the diagonal value, I can always go to the not diagonal value either by changing covariant component or contravariant. And equalizing these things, we will get our, because equalizer is solved, but it's a solution to universal problem. Quest C is one. For equalizer of, here we will take not product but co-product of diagonal values. Here we will take co-product over functions. In fact, morphisms in category C. But here is a distinction. I need to switch. So here was first component domain and codomain. Here should be codomain, then domain. And arrows are getting in an opposite way. You can get the statement just by dualizing. So co-products go to co-products, equalizers to co-equalizers, arrows are altered in the sides. So codomain becomes domain becomes codomain, codomain becomes domain here. And the arrows are co-product over F as C, here is co-product over F. Where again F is from C to C prime. Okay. Property number 4. What? That's commute with costs continuous and commute is continuous, points is co-continuous. Well, that's obvious since we can express end and coend as limit and colimit. Well, by the way, you never asked me when the coend or end does exist. If this category T is complete, so of course it is. That's all. So, as you remember, we are taking limit, and limit exists if, so limit will exist if all the limits in category D exist, and category is set to be complete if all limits exist. So coend and exists if D is complete, always of any factor C op cross C to D, and coend exists if D is complete. And now, since we can express them in case when it's true, we can express them ends and coends as limits and colimits. So continuous or co-continuous functions respectively commute with limits and colimits respectively. So here the property number 5. Well, I don't have space. 5 here. I need to clean. Convenience theorem. Here will be Houdini theorem as we used to have it in measure theory, multidimensional calculus. It will be about ends and coends as integrals, right? So we have f is a function CO cross C EO cross E. So we will be taking ends and coends with respect to pair of variables. So for every variable, we need to have a category and its opposite. And we again let in the category. One of the then the other so n over pairs CE pairs pair C here will be n over D n over C n over C n over E. Same for coend. I'm just lazy to write coends instead of ends. Now will be property 6. But before state property 6, I wish to remind you the following thing that I was talking about in lecture about the jump. Lecture about the jump. So before talking about 6, let's recall something. So remark. So let category E has all products and co-products. Then for every xy belonging to D, for every set S belonging to set, we have the following. morphisms from coproduct over set S of object X to object Y are in bijection with morphisms from object X to a product so many times as element in set S of object Y. Well, there was third adjunction, but I don't need it right now. So how we can think about this? Guys, how we will think about it? That if we have maps from X to Y, from X to Y, from X to Y, here will be S1, S2, Sn. Then we can arrange them in two different ways. So case A, I will write Y, here will be X, X, X. Here will be S1, here will be map S2, here will be map Sn, right? But maps with the common n starting by just with a map from coproduct to Y. Okay. B. I can arrange these maps because they have the same domain as a bunch of maps from X to Y, Y, Y. Here is 1, here is 2, and here is N. But this is in a bijection with a map from X to product over S of Y. Because maps to product, it maps to component. Maps from a product, there are maps from components. By definition. So I have these two ways. So bunch of maps indexed by certain set S can be arranged either this way, either that way, either just lay all together in one big box, doesn't matter. This gives us this adjunction. Now, notation. Before I use power and copower, I will again use them as power copower, but I want to change a little notation. So, as tensor X, I will denote as coproduct over X, coproduct over S, object X. And cotensor, such pitchfork pointing down, object Y, will be product over S of object Y. So if U cross C D is a factor, D is an object of has all products plus co-product. Morphisms from the coend of factor F to object D are in a one-to-one correspondence between the natural transformations U cross C from factor F, which I'm writing where it has variables. First above, second below, to C. Conversely, second above, first below. For tensor And another one, natural transformation, CO cross C, D, from a function C, blank, double blank, tensor T, function F, are in one-to-one correspondence between the morphisms category C from object T to the end of function F. So we got two adjunctions, and they look the following way. That coend acting from O cross T to T is a joint, is a left adjoint of a function. So I put it instead of D. In certain books you can see instead of blank or empty spot. And another adjunction. It is from C and question mark. U. Very nice. Therefore, in case when category T has all products and co-products, in particular when it is bicomplete, so it has limits and qualities all, then you can auto juggle between your ends and coends inside homesteads. So you have a jump. Using this adjunctions, Fubini theorem can be proved much more easily than using super bulky stuff about wedges and co-wedges. Well, examples of coends and ends will be seen now for the next lecture, even maybe today. Every single time. So right now, part 2 of today's lecture will be coend calculus. So it's and coend, so I will write just coend calculus. In my personal opinion, which is certainly biased and not true, coend calculus is the most efficient and powerful tool in modern category theory, either enriched, either unenriched. It's ubiquitous, it just covers everything what you need. It's a calculus. It's so natural as if you were using plus, minus, and multiply for integers. You can't escape from it. So everything what you do, this or other way, is described by answer way. Of course, not everything completely, but the totality of majority can be described by coend. So rule number 1. Interaction. What is it represent? So E which means that coend can be taken from contravariant component as an n. And second one, Ends are getting out the covariant component as ends. So covariant home preserves ends, contravariant home converts coends to ends. How we will get it? Limits and colimits commute with continuous functors. Both home as a covariant as a contravariant are continuous, because contravariant home is a covariant home in an opposite category. It is continuous because second variable. Yes. That's it. Second. Natural transformations is n. So natural transformation. Functors. Going from category C to category D. And you see, I'm just writing the formula. From this formula, I can derive. Knowing that this is the notation for functor category, therefore, in parentheses, and I'm going to home set. In home set, who are arguments, functors, from where to where? From C to D. So I just don't need to write all this bulky stuff. See, in this formula, I can always recover who is who. In an end over C, in a home set D, from FC to GC. Isn't it beautiful? So before, when we were talking about natural transformation, we were looking for maps from FC to GC such that they are making many squares to commute. When we are taking n, they all will extract and how I would call it, like join them together, the families that constitute natural transformations. Here is a super powerful thing. Always you can write functor category, homonym functor category as an n. 3. Well, 3 is Yoneda lemma. That's a true Yoneda lemma. There are other authors that use notion of Yoneda just whenever they think that if something switched in Yoneda lemma, then it immediately becomes co. No. Because Yoneda is related to n, so Yoneda should be related to n. In Yoneda lemma, we have what natural transformations from representable functor to a given functor will be given by certain n. Okay. In Yoneda lemma, on this side, we'll be stating co-end. That's why in trouble. So here I'm assuming that f is a covariant function because they will give two versions. And g is contravariant. Sanders-McLean in his book Category for Working Mathematician referred to Yoneda lemma about very different statement, referred to Ken, Daniel Ken, who's Ken extensions, Ken complexes, and so on. And this is not related to this stuff. What I will write now down immediately and one-to-one generalizes to enrich context. What written in McLean's book has nothing to do with what I will write now. And it cannot be generalized so easily or straightforward into an enriched context. So even for what is enriched context? Forget landing in sets, landing in abelian groups. Then all factors are getting additive, home sets are abelian groups, and so on. Will it work there? I have no idea. Or in simplicial sets we are ending. You'll have classical homotopy theory, what they do. Will this work? I have no idea. But the formula that I will write down work 100% known. Okay. So when we are making, let's call it the proper way, convolution between a representable functor and your functor, nothing changed. You are given a functor. When you are looking for natural transformations from a covariant functor to your functor, nothing changed. You're getting a new functor. You see here blank. Instead of this blank could be written letter x, and this x will be here. So f of x, and here we'll put x. So this blank is an argument of your f or g respectively. So the main thing that here c is covariant and f is also covariant. In coend, c is covariant and here c is contravariant. Very important, because always you're taking n to coend when you are trying to take it to compute it. You should 100% be sure that one of your variables along which you take n to coend is covariant and other is contravariant. Always check it. If you do something else, it will be completely mistaken, wrong statement. It will be not even red herring. It will be nothing. It just doesn't exist because your arrows will be all broken. First part is co-uneta because second is uneta. So this and this, using property number 2, are the statements of uneta lemma. Therefore, going to dual case, to coends, you're getting co-uneta. So co-uneta is about tensoring, and uneta is about cotensor. That's what, if you want to say that. There are more rules of coend calculus, which I can't write today, because we haven't studied weight limits, colimits, and Ken extensions. We haven't studied tensor from cotensor situation, profactors, and whatever. They will be from now everywhere. So limit and colimit, I just want only to conclude, are, I would say, the most efficient ways to describe in the same language all the species. But before you will shut your notebook and close your eyes after this tiring lecture, finally you won't see me again in person. Yes. I want to emphasize that all this is cool, very cool, with one exception, that end and coend are coming with the natural transformation, which is universal. So by these all formulas, you recover the object, then transformation. You need to think about this with your head, and a little sometimes get your hands dirty. That's not so difficult, since we have the adjunction. Okay, since we will have this adjunction, that's not getting so difficult. But still, you need to think about that. So if you will take instead of t the coend itself, then to identity here will correspond to something. And that something will precisely give you what you need. The same as for adjunction when you have unit and quick. So never be super excited if you really need to write down the natural transformation, as in any situation. Unfortunately, coend calculus will not give you like in one shot everything like this. I mean, maybe it's given, but if for computer it's a one like kick, for you it will be half day of work, or maybe even half life. So it depends what does it mean easy and for. But still you have right now these 3 rules, and every time will get more. So what is next time? Next time will be remote. I will send everybody a link. I mean, it's already available on Canvas, but I will give everyone again a direct link. Will be monoidal and enriched categories, very basic statements. We don't need to go deeper, but we just need to say what is an enriched category, natural transformation, enriched factor, representables, and like give very few examples. Nobody is obliged to think about enriched categories a lot. Just think about your favorite category, whichever category you'll pick up. I'm sitting in your head. I will say that's enriched, at least by usual set. So I'm wishing you all a good end of semester. And next time we'll see online and finish this course also online. My apologies if something was wrong or I kept you a couple of times really long. So thank you for your attention again. Goodbye. Thank you.